Please welcome Don Box, Microsoft Distinguished Engineer.
Hello, Shenzhen! Welcome to WinHEC. Come on in, plenty of room. My name's Don Box. I work at Microsoft. I'm in the operating systems group. I work in the development team on silicon graphics and media. Prior to that, I ran the engineering team that built the Xbox One operating system. What I'm going to do in this session is bring some technical depth and perspective to the way Windows works to tee you folks up for all the sessions that you're going to be going to through the rest of WinHEC. I know some people in this room have not been exposed to Windows, so this in some ways will be a technical overview for how the platform and the operating system is put together and how you as a hardware vendor or a silicon platform or ODM or OEM should be thinking about the product that we're building. I'll also be talking about some new things that are very specific to Windows 10, and I'll do my best to make sure that those are obviously new and different from what we've done in the past in Windows 8.1. So without further ado, let's get started. What I'd like to do is walk you through the journey we've been on getting to Windows 10. And the best way to understand that journey is to look at the beginning of this decade back in 2011. In 2011, Microsoft built 3 products that had very distinct operating systems. We had the PC business, which ran Windows, and by 2011, we were already on the converged Windows NT code base, Windows DOS, all the DOS-based Windows were gone, and we were on a very nice progression building on the Windows NT code base. But we had 2 other products that are interesting to observe. A second product we had was Windows Phone. Windows Phone in 2011, again, that was at the beginning of this decade, was running a completely different and distinct operating system that was based on this thing called Windows CE, or WinCE. Windows CE had some surface level similarities to Windows NT, but completely different code base, many, many different fundamental assumptions, and we, as Microsoft, had 2 significant code bases that we had to keep going on. A third product was this product called Xbox 360, which many of you still may be using, right? Xbox 360 is a very popular product. Xbox 360 was running a fork of an older version of Windows NT from about 1999. So the Xbox 360 was running an old, wildly divergent branch of Windows NT. So the PC and Xbox both were NT-based, but over time, the code bases diverged. Windows Phone running a completely different code base with no relationship whatsoever. So we as Microsoft had these 3 products in market, which we were continuing to invest in and continuing to evolve. But we had 3 code bases we had to maintain. And what we found, 2011 was a very, very interesting year. Because in 2011, we tried to have this ability to write applications that spanned those 3 devices. And we did things, for example, to try and bring Internet Explorer to all 3. And we had to do very, very difficult, unnatural, untidy, unclean things to get Internet Explorer to run on those 3 wildly different code bases. So Microsoft, as an ISV who was using Windows, when we were building these upper-level components, we had a heavy engineering load in order to bring Internet Explorer to those. Or another thing we tried to do in 2011 was to bring Silverlight, which was our application platform that we were using across these devices. Bringing that to Xbox was also just a very difficult task for us. And so we observed in 2011, we can't keep going this way. And so what happened was, between 2011 and 2014, when we shipped Windows Phone Blue, we've been on this progression of bringing our code bases together. And so Windows 8 and Windows 8 and Windows Phone 8 was our first salvo where we replaced the Windows CE-based OS underneath Windows Phone with a Windows NT-based one. So we had a converged kernel, but a lot of divergence up top. With Xbox One, which we shipped in 2013, we have the 360 code base. We stopped working on that for Xbox One, and we started over from the Windows 8 code base. So we had this moment in time where Windows phone, and Xbox were on the same code path, but we still had a fair amount of divergence and independent evolution of the code. So with Windows 10, what we observed is we might be on a path, leading into the Windows 10 planning, that if we weren't deliberate, we might be on a path towards divergence again, and we'd be back where we were with Xbox 360 and with PCs. But more importantly, we saw that the business required us to support even new form factors which we had not contemplated prior to this, right? We have this product Surface Hub, which is the giant touchscreen, right? That needed an operating system. We have HoloLens, and I'm sure many of you have seen videos of the HoloLens, the holographic headset. That needed an operating system as well. And then one thing we'll be talking about a fair amount at this event, which is the IoT space. The IoT space needed an operating system which was tuned to a very small form factor and very low resource requirements. And so when we figured out what we wanted to do for Windows 10, we looked at these business requirements, which is, wow, we have 1, 2, 3, 4, 5, 6. I can't hold up 6 fingers, but there we go. We have 6 products that we need to go support a single operating system on. So we need to really, really be planful with how we do that. And so with Windows 10, we're making a commitment to bring everything together so that we have a single core OS. We have one core OS which runs on all of these device families. We have a common app platform and a common device platform to enable application vendors, ISVs, to target one platform and get the reach across these 6 different device families that we're talking about today, and any future ones we'll dream up after we leave this event. And also one store, right? One store allows the consumer to be able to buy a particular item, an application, a game, a piece of DLC, and be able to use that across all of the devices that run Windows, that run Windows 10. And so this is kind of framing the way we think about Windows 10 back in Redmond. And this reflects a technology direction. It represents a product strategy direction. And it is at the heart of everything we do on Windows 10. This enables us, of course, to dream dreams we weren't able to dream before. So as you can see, with a single OS, we're able to bring that to bear to satisfy all of these form factors, which we're talking about a lot throughout the year, and other form factors which we'll dream up and that you out there will dream up as well. Right? So we're really trying to get to a single operating system that supports all of the device form factors we're going after. Now, I keep saying one OS. Now, you might be looking at this and saying, the user interface for some of these devices is wildly different. Right? The user interface, the user experience that one has when they're wearing the HoloLens is going to be fairly different from what they see when they do Surface Hub, or when they're using their phone, or when they're using their PC. So what I'd like to talk a little bit about is how we actually construct the operating system. This is the way Windows 10 is built. We have one core OS which we deploy to every single device that runs Windows 10. If it is running Windows 10, it is running the same core OS, it is running the same application platform, it is running the same device platform, and all of the libraries and frameworks and runtimes are all the same. To make sure that the operating system we are building is tuned to a particular device and a typical form factor, we add additional components when we put that OS onto a PC so that it has things like the start menu, the familiar mouse and keyboard experience, and so that it can run Windows desktop applications. Because as you know, we have 2 decades plus worth of Windows desktop applications out there that people love to run. Right? Everyone in this room probably has a Windows desktop application that they feel like they need, either to enjoy their life or to get their work done or what have you. So when we put Windows 10 on PCs, we're deeply committed to keeping those things running on PCs. And so we bring in the additional OS components to go make those things work, as well as the shell, the interactive experience that does that. On phone, we add things to keep the existing Windows Phone applications running. Right? We've sold many millions of Windows Phone applications. Right? Those will continue to run on Windows 10 for phones. We also have telephony. We have the touch-oriented shell, and a variety of things that make a phone a phone. And those things only ship on Windows 10 when we put it on a phone. On Xbox, we obviously are committed to the 10-foot experience. We're committed to having multiple people simultaneously looking at the screen and playing a game. And also all of the Xbox One games and all of the Xbox One applications that people have bought, we're committed to keeping those work. So that's the way Windows works when it's on Xbox. And then finally, that last box, every time we dream up a new device family and we decide we want to make Windows great on that class of devices. So for example, let's say we wanted to have a Windows 10 knee pad. Like we wanted to say there's a great way to have a knee pad that's going to be Windows powered. Right? We would have a new box up there. It would still be the bottom. The bottom would be the same Core OS across all products. But we would layer special knee pad specific functionality to make it the best knee pad ever. We are not announcing the Windows 10 knee pad at this event. Now, that previous slide showed you how we think about composing or building the operating system. One Core OS, additional device-specific additions on top that bring in new functionality for that device family. What I'd like to talk about is the value this brings to bear to ISVs, to software developers. That approach that we are taking gives us the Windows Universal App Platform. And we started talking about that a couple weeks ago at MWC, Mobile World Congress, and at GDC. The advantages of having a universal app platform is that we have the ability to have a common tool set, a common set of APIs, a common store, a common platform, as well as machinery to allow us to write an app that lights up in the appropriate ways depending on the form factor. So if you think about the previous slide where we talked about a Core OS with form factor specific binaries on top, we actually have the ability to do that for your applications as well. So you're able to say, I want these assets, 4K bitmaps for my game. I only want those on my Xbox or on my large screen PCs. I don't want them on my phone. Our app platform has the ability for you to structure your application so that the assets that are needed for a particular form factor are only deployed to that form factor, and they don't have to be carried everywhere else. Otherwise, the download side to put all of those on a small phone might be a little bit expensive. We've talked a fair amount about the app platform already. We'll talk a little bit more about it in this talk. But what this talk is really about, and what WinHEC is really about, is the device ecosystem, the hardware ecosystem, the silicon ecosystem. So the approach we're taking to building the operating system yields the Windows Universal App Platform, and it also yields the Windows Universal Device Platform. And this is very much a value proposition for the hardware and silicon and device ecosystems. And so what we get from the common device platform is common development hardware, right? If you are building a peripheral, if you're building a new piece of silicon and you're doing bring up, we have a common set of hardware that you can go off and bring that up independent of whether you're building a phone, a PC, an IoT device, a set-top box, whatever you might be building, common development hardware that works on all of those things. We also have a common validation suite so that when you build your driver or your device configuration, you can then go validate it, and that machinery works across whether you're building a phone, a PC, an IoT device, etc. Again, just like with the ISVs, we have a common tool set. So you go to use Visual Studio, common SDK, and you only have to download that once for all of the device families you need to support. That's different from Windows 8.1, where we had a very siloed approach. Again, common hardware dev center, so you can go in, grab all of the information you need, the samples, the SDKs, etc. And then finally, we've done a lot of work to make sure we have a consistent DDI and a single development kit that you can use to develop drivers and device configurations for any kind of device you would want to build with Windows 10. So most of the rest of this talk is really talking about the Windows Universal Device Platform. And a large part of that is related to building device drivers, but also accrues to some other aspects of device creation as well. So with the Windows Universal Device Platform, you as a hardware or silicon vendor are able to develop your drivers against a single API and a single DDI. This means you get to write the code once, and you build it once simply per instruction set. So if you're supporting both 32-bit and 64-bit Intel instruction set, you'll build 2, not 10. So that same driver for x86, for x64, and for ARM32, those are the 3 drivers you would need to build if you wanted to support everything. Right? You don't need to build a separate driver for phone, then for PC, then for IoT, right? one driver for all device families is the model we're going with Windows 10. And that driver obviously can go run on every possible device we run Windows 10 on. Now, because you're going to likely go to many sessions at WinHEC over the next couple days, and a lot of three-letter acronyms, TLAs, will be thrown around, I'm going to walk you through kind of the basic platform of Windows 10 to make you familiar with all the subsequent talks you'll see, as well as some of the demonstrations we're going to do in a few minutes. So the first thing I want to talk about very briefly is how the app platform works, just for a moment. So in Windows 10, we have this notion of a universal app platform, and the apps that target it are called Windows apps. Sometimes we say universal apps, but we call them Windows apps. And a Windows app can run on every device family. So a Windows app can be written, and it will run on phone, PCs, Xbox, IoT, and other devices like HoloLens. That's in contrast with Windows desktop applications. On PCs, we still continue to support the 2 decades plus worth of Windows desktop applications for running them on PCs. And so sometimes in a technical session, we will talk about a Windows app and a Windows desktop app. Windows app runs on all devices. Windows desktop app, PC only. This table shows you a bunch of the differences. You can look at this for your reference, but I want to make sure we understand Windows apps run everywhere, and we still continue to run Windows desktop apps on PCs. Now, I'm assuming most people in this room are in the hardware or silicon or device business. And you may be asking yourself, is an app good enough? We expect your communities to go off and write lots of apps, right? Anytime someone builds a device, there are apps that are very device specific that come along with it. If you're an OEM, say a Lenovo or a Dell or a Nokia, you're off there building apps that are very specific and exploitive of your device. We expect that to continue to happen, right? So you are definitely, everyone in this room is effectively an app developer. You're also something else too, right? So as an app developer, that previous slide matters. We expect by writing Windows apps, the universal apps, those apps will be able to come with you on every device you're going to go build. That stated, there is a role for drivers. An app cannot do everything. There are certain capabilities in terms of access to the hardware that require you to go off and build a driver. And so here's a list of some of the things that might make you say, an app is not sufficient. I will write an app, but I also have to write an accompanying driver. And so the most common one, which everyone intuits, is that if you want direct access to physical hardware, that has to happen in a driver. If you want direct access to IP blocks on the silicon, say if you're a Qualcomm or an Intel, right, you have to write drivers to go access specific IP blocks. If you want to integrate with the device ecosystem, that is the low-level device ecosystem like the I/O manager or the device tree, those things are all done as drivers. And if you're adapting your hardware to existing APIs, like if you're writing a network interface, a NIC, right, we have a full stack with things like WinSock to plug in, you write a driver. If you're a graphics person, you've got a graphics card, you want to plug into DirectX 12, which we saw some really great demos in Terry's keynote, that also requires you to write a driver. So this is a good list of the things that might cause you to write a driver, but you'll still be writing applications. And often what we see is this pairing of the application, which actually exposes functionality to the user, is paired with a driver that is deeply integrated with the hardware to get its work done. Let me say a few things about how Windows drivers work and what the taxonomy of a Windows driver is. It's actually pretty simple. A Windows driver is simply an executable that exports one function called driver entry. And so if you are going to go write a device driver on Windows, you are going to compile a binary, and it will have one export, driver entry. And when your driver is loaded by the kernel goes in there, and it calls into driver entry, and it sets up an object with a dispatch table, and away you go. So that's what constitutes a driver on this platform. We'll talk more about APIs and DDIs in a second, but there's a few kinds of drivers which are useful to know, and that thing I just said is actually fairly universal to most operating systems. But the next few things are very Windows specific, so let's make sure we understand them. In general, we don't want everyone to have to go write a driver. It's a little harder to write a driver than to write an application, right? And we want to lower the cost of people bringing devices to market, so we don't want to make you write a lot of code. So we have a set of drivers which we call class drivers. Class drivers are drivers that we just build into Windows. We build them as drivers the same way you build them as drivers. But the class drivers build in functionality for hardware that's been standardized. So things like certain buses, which are very standardized, the hardware interfaces are standardized. We simply write one driver that works on all platforms, and we put it into the operating system. So if you see that there is a class driver, you should try to use it because we've got one in the box. It's been tested, validated. It's probably been around for many, many years. And unless you've got real need to differentiate, our class drivers are typically sufficient for your devices. There's a base driver model, which is very wired into the way the I/O subsystem works. But various domains like networking or graphics define these things called mini-port drivers. And so if you write an NDIS driver or a graphics driver, those are mini-port drivers. Those have a very restricted subset of things you have to do. So you'll hear the term mini-port sometimes. And then finally, we have this technology, which we've had around for several releases already, called the Windows Driver Frameworks, WDF. And WDF up-levels the overall experience for the driver developer so that the set of abstractions you have to deal with are simpler, and some of the more complicated aspects of writing a driver, like integrating with plug and play or integrating with power management, right? Those things are very hard to get right, and we've actually codified them and put the best practices into this framework, which we call WDF. And WDF has an additional benefit. In addition to making it simpler to write a driver, it allows you to write a driver that runs in both kernel mode, protected mode, supervisor mode, as well as in user mode, where the applications work. So it actually increases the reliability and robustness of the system if you write a user mode driver, because when it crashes, it doesn't bring the entire system down with a blue screen, which we don't like blue screens, right? Instead, it just causes a process crash, which we can recover from. So here's a picture of how it's all held together. Like every operating system people are familiar with nowadays, we have a kernel mode and a user mode. The kernel is built as a binary called entosKernel.exe. Those of you who have a Windows device, you can go find this file. If you want to know what the kernel is, that's it. Single file, there's your kernel. The kernel has some capabilities like an object manager, I/O manager, memory management, scheduling, process management, etc. That's what those green boxes are. And that kernel has been with us for a very long time. We shipped that kernel, the first version of that kernel shipped in 1993 with Windows NT 3.1, and we've just been working on it, grinding it, sanding it, getting it all nice and polished. And it's been a really fantastic asset for the company. So when people say the NT kernel, it's because it says NTOS, right? So it's the NTOS kernel. Now, the NTOS kernel is extensible. It's extensible through these things called drivers. Those are those executables with driver entry. There are two kinds of drivers at this level of architecture. Kernel mode drivers, which run in the same privilege level as the kernel. They have unrestricted access to the internal data structures of the kernel, which means they are the most flexible, but they are also the most susceptible to bringing the system down. So the kernel mode drivers, right, have unrestricted access to the system, and definitely an important part of our platform. User mode drivers, which are the guys up on top, they look the same. You write them the same way. You still write a driver entry. You still have a dispatch table, all the things you do for a kernel mode driver. But instead of running them down in the address space of the kernel, we run them up in their own private address space, up in user space, just like an application, right? And so when those guys go down, when those processes go down, it's just a process termination. System keeps running, no blue screen, no crash, it's much better. We also have these things called scum-based services. If those of you who come from the Linux world or the Unix world know about these things called daemons, we have our own version of daemons, which we call scum-based services. Services basically are processes that are managed. They get booted up typically automatically or on demand, and they provide background services to drivers and applications. And then you'll finally, pulling it back around to our app platform, we have Windows apps and Windows desktop applications. Windows apps are the universal ones. Desktop applications are PC only. Now, moment of pause. This slide, except for that upper red-hand box, those red boxes, this slide is true for phones, PCs, Xbox, IoT, everything. The red box upstairs is PCs only, right? So if you're running a PC, we run desktop applications. We don't run them on phones or Xboxes or et cetera. Great. Now, everyone in this room is going to works at a company that is likely to go write applications and is likely to go write drivers. Here's a good way to kind of think about interacting with Windows. So Windows has an API and a DDI. The API, Application Programmatic Interface, is the surface area of the product that we expose to apps. Application developers, ISVs, write apps and they write them against the API. And we'll talk about how the API is structured in a moment. Driver writers, who are interacting with the system from the bottom, next to the hardware, they interact with the system through DDIs, device driver interfaces. So Windows has a DDI and it has an API. Well, they are distinct. Apps typically don't see the DDIs. Drivers typically don't see the APIs. So we have two sets of interfaces depending on what role you're playing. Now, one aspect of Windows is that we support independent deployment of applications from the operating system, and we support independent deployment of drivers. So in order to allow a driver to be deployed independently from the OS, all of these things use something called an ABI. They adhere to something called an ABI, Application Binary Interface, which are simply rules for how we call across units of deployment. So the API is an ABI, and the DDI is an ABI. And this turns out to be important because we need the ability, once we put the OS out in the field, to be able to independently push new drivers out, and once the drivers are already deployed, update the operating system. So by using an ABI between the drivers and the OS, we have the ability to independently evolve both the drivers that are deployed out into the field, as well as the operating system itself. Right? And this is a fundamental way that Windows works. The Windows DDI is the way that drivers interact with Windows. There's a single DDI that spans all device families. So in terms of having a universal device platform, we have a single DDI that is available everywhere. Kernel mode drivers only are allowed to see the DDI because they're running down in the kernel. Right? All they can see is what the kernel exposes. A user mode driver, which we talked about briefly, a user mode driver sees both the DDIs as well as some set of APIs. So let's talk a little bit about APIs and then we'll go do a demo. On Windows, our API has different entry points that come in 3 different flavors or patterns. So we have 3 different patterns for exposing functionality to applications: Win32, COM, and WinRT. This table gives you a good reference. Win32 APIs are C functions that are available to C and C++ programmers. COM adds the ability to have interfaces and objects, and it is also available to C and C++. And then finally, WinRT is an API style that allows us to expose interfaces, objects, and classes, not just to C and C++, but to all of the languages we support on the platform. So if I have an API in WinRT, I can get to it from C#, from JavaScript, from Visual Basic, and from C and C++. So you can see that for each of the kind of scenarios, like a Windows app, or those of you who are writing user mode system code, like a user mode driver or an entity service, or if you're writing desktop applications, these technologies, COM, Win32, and WinRT, are available everywhere. But we limit what's available depending on the context. The most important thing I want to take away from this talk here is those bottom 2 lines, right? We have this library that allows you to write system code, drivers, user mode NT services, against a single API that spans all of our devices, right? And there's a single static library that you simply link against called onecoreuap.lib, and that is the surface area that's available everywhere. And so when you write a universal driver to be deployed everywhere, you want to make sure to use that as the target surface area, which will keep you within the limits of what we support everywhere. As you know, Windows PCs, the desktop operating system, has been in market for 22 years, right? NT 3.1 shipped in 1993, if I have my dates correct, right? That's a lot of time. There's a lot of code in there, right? And we continue to keep that code going and continue to make that code better. But most of that code does not come to HoloLens. Most of that code does not come to our phones. So if you want to be in the aspect of Windows that is everywhere, that middle one that kind of dictates where you're at. For system code, and then for apps, the top one is yours. Right? And system code gets a little bit more access than apps. All right. I feel like we're close to doing a demo. So you may be saying to yourself, Don, this is all very fascinating, but how do I write code on your platform? So what we should do now is write some code. The way we write code here is we go get Visual Studio. Visual Studio is available on the web. You can go get the Community Edition right now. It's free. Install it. You can then also get this thing called the Windows Driver Kit, which is an add-on. It sits on top of Visual Studio that allows you to go write drivers and do all of the device machinery that we're going to talk about in this talk. And then finally, when you make your new driver, you'll notice that we have three kinds of drivers you can build. Universal drivers, which is the new kind of driver that we're supporting for Windows 10 on every single Windows 10 device. But we still support Windows desktop drivers. So if you have an existing desktop code base, you can bring that over, no problem. And Windows phone drivers. So if you have phone drivers already out in market, you can bring those in and use the WDK. So we have a single WDK that continues to support all of our existing platforms, but the universal driver is the way we're going. So, without further ado, I believe we're going to do a demo. Patrick. Typing my own password into his account does not have the desired effect. While Patrick and I work closely together, we have distinct passwords. So thank you, Patrick. So here is Visual Studio, and this is looking at a universal driver project that we're going to be using throughout this talk. And what this project does is it builds a universal driver as a UMDF driver. And what we're going to do is we've got a UV sensor, a 3512 sensor. It's a part number. And we're going to write a driver to make that driver accessible, that device, that UV sensor, available up to our application. And remember what I told you when I said, what is a driver? It's a executable with a driver entry. Well, there it is right there. So there's the driver entry. And what I'm going to do is go over here. And you'll notice that it's a single function. We just do one function call, which I'll talk about later. But what I want to do is go build our driver. So I've told Visual Studio, go off and build our driver. I've already got the WDK installed. It's compiling, it's linking, it's building a binary, right? It's then packaging that binary up. It's signing it, making sure that I've got a nice package that I can then go put on my devices. So my driver just compiled, and that bottom makes me happy. When I see 0 errors, 0 warnings, I always feel like, you know, it was a good day. So now what I want to do is show how a universal driver differs from a desktop driver. So what I'm going to do is go in here, and I'm going to add a new call to a function. And I'm going to pick a function that is only available on desktop. This function is not available on phone, it's not available on Xbox or IoT, and that function is one that is not really a great function to call from a driver, but we'll use it anyway, which is message beep. And what I'm going to do now, save the file, and I'm going to rebuild my driver. And so now what's happening is we're going to perform extra validation because it's a universal driver. And in this case, it will actually compile. But what you'll notice is as we're off validating that it's in fact a universal driver and that we can sign it and deploy it to all of our devices, we get an error, right? And that error is telling us API message beep is not supported as a universal API. And so now I have two choices. Choice number one is to say, well, look, I need that capability, and I'm only going to make this driver work on a desktop, only on PCs. This driver doesn't need to work on phones, doesn't need to work on IoT or anything. And to do that, I would go here and say, on my driver settings, change it from universal to desktop, or to mobile if it were a mobile API. This happens to be a desktop API. Or I can say, no, I really need it to run on all those platforms. And I simply remove it and rebuild. And momentarily, this thing will come back with a sign and a success. Now, we're going to look at a little bit more code throughout this talk, but there's one piece of code I want you to look at right now, which is if you look at our driver entry, it's actually pretty minimal. Very, very small driver entry. The reason our driver entry is so small is because we're using WDF. Remember when I said we have this framework, the Windows Driver Framework, which really up-levels the experience for writing drivers? And so all this driver does to get started is it calls WDF and calls WDF driver create. And that goes off and builds all the infrastructure and integrates with the rest of the operating system. So I can focus on the things that make my device unique, not a bunch of generic plumbing I have to go interact with that really aren't differentiated business value. So let's go back to the slides. So WDF is used by that driver. It codifies a bunch of best practices. And up until Windows 8.1, up through Windows 8.1, WDF was just yet another operating system component, right, that we built as part of the operating system, that we shipped as part of the operating system, and that was opaque to you, the driver developer. So what that meant was, while it made your life simpler, if something happened, like if you had a crash or you were debugging, right, it was very hard for you to understand the interactions between WDF and your code. Additionally, because WDF actually codifies a bunch of best practices for the overall driver developer ecosystem, that knowledge wasn't being shared because you couldn't look at the code. All you could see was the binary. So what we're announcing today is we're actually taking WDF and we're making the source code available through GitHub. Thank you. So today, you can go to the URL I have up here on this slide and go actually download the sources for WDF, put them on your machine, and Splunk, understand. And honestly, you don't even have to go to GitHub, because another thing we're doing is we're actually deploying both to the symbol server and to the source server. So if you configure Visual Studio appropriately, we will go download the sources for you automatically while you're in the middle of a debugging session. It will grab those WDF sources. You can step through them. You can go see what the stack frames look like. And so we feel this is really a big move for us to kind of help the driver ecosystem be more productive and build better drivers. Let me just quickly walk you through this. Can we go back to the demo? Awesome. So, awesome. So here's our driver entry that we looked at a moment ago. And notice I've got that function, WDF driver entry. That's my initial entry point into WDF. What I'm going to do is go to my web browser. And I've already surfed to the WDF website. I'm sorry, to the GitHub website. So there's a WDF page on GitHub. This is the link that was on that slide. And you'll notice that we have obviously some material that tells you what WDF is and why you care about it and how to go use it. But of course, we also have access to the source code. Now, I watched Terry's keynote, and I know that the internet may not be completely reliable in this room, but I'm going to tempt fate and try and surf and go find our function. So I'm going to go to the sources. Thankfully, I was prepared. Prior to coming up here, I pre-browsed to that page. One of the great things about doing coding demos as opposed to the really fancy demos that Terry does is I just need to show you some text and my demo is done. So I have an easier job than Terry on a number of fronts. So here's the body of the function. You can just go look at it on the web inside of a browser. You can go download the sources to your machine. You can go, we'll go grab them for you automatically from Visual Studio. And you can see any mystery that there was around that function, it's gone, right? And you can see that a lot of what we're doing at Microsoft is we're really trying to embrace the availability of source code to help make the ecosystem successful, and this is just one of the steps we're doing along the way. Awesome. When we talked about the Windows Universal Device Platform, we talked about one of the characteristics being a common hardware development platform. One of the things we've really invested in the last year or two is making sure that the various hardware and silicon constituencies, both the silicon vendors, the IHVs, the ODMs, the OEMs, and the maker community, all have the hardware they need to go off and develop on the Windows platform. And so, as of today, we now are able to talk about supporting both instruction sets, the ARM and the Intel instruction sets, having dev boards available for that are suited both for makers, but also for people who are building peripherals, people who are building sensors, cameras, right? All of these things require an open dev platform that you can then go off and basically do your hardware hacking and your hardware bring up. And these things are all broadly available, and let's go walk through what they are. On the Intel side, we have two boards that we support Windows on. One of them is called the Sharks Cove board. The other board is called the MinnoBoard Max board. They both run Atom processors, the Bay Trail family. They have different capabilities, which you can see up here on this slide. And both of these boards run our various Windows editions. So I can use these boards to do IoT work. I can use these boards to do prototyping on the desktop OS, right? So any place I've got an x86 build of the OS, I can put it on this machine. I'm sure you've heard we made both Broadcom and Microsoft have been talking about Raspberry Pi, right? We're also supporting Windows on Raspberry Pi. Here you can see the hardware specs for Raspberry Pi 2 board. And we have an entire session called Building Devices with Windows IoT that's being given by Steve Teixeira tomorrow. I suggest you go to that. It's an awesome session. And he'll be talking about Raspberry Pi in that session. And then last but not least, there we go. Terry talked about this in his talk. I'll be talking about it and showing it to you. Our friends at Qualcomm have partnered with us, and we're bringing out the Dragon Board 410C, which is an 8016-based Snapdragon part. And we're supporting Windows on this board as well. This board isn't available today. It'll be available in the summer sometime. And we will be right there with Qualcomm supporting Windows on this board. And there's the specs. Now, what I'd like to do is that driver that we were looking at, I want to go look at the code one more time, and then I want to go see that code running on some of these boards. So why don't we go take a look at Visual Studio ever so quickly. So here's the same project, just with a couple of different files open. So what we're going to do is we're going to build a universal driver. That's what we started looking at. And then we're going to build a universal app that uses that driver and then builds an overall experience on the device. And so the driver talks to a UV sensor, which is a 3512 sensor. That's why you'll see 3512 in all the file names. And so our driver goes off and talks to that and then serves up data samples off the UV sensor into our sensor stack. So Microsoft has a sensor stack, right? Our sensor will interact with our sensor stack interacts with the driver to go get our samples. And then it surfaces up through APIs, right, to a universal app. So the driver code is here on the right. And you'll notice we simply make some DDI calls. So calls like I2C sensor read byte is a DDI. It's part of the Windows DDI. It's available on all of our devices, right? We make a couple of system calls. And then finally we basically have read the data, it into a ushort, and then pop it up to Windows by calling that last DDI. That's the driver side code. The app side code, this is a universal app code fragment we're seeing on the left. What this does, this C# function gets called every time a sample is made available, and we simply go grab the reading, which is that same data type the same data we passed over on the driver. We go add it to a data structure that our user interface is working with, and then we just render it. So what I'd like to do is bring Holly out, because it would not be a WinHEC keynote without Holly coming out. And I'd like to go show this single app and this single driver running on a couple of devices. Hello, Holly. So let's start with, there we go. So let's start by looking at the Sharks Cove. The Sharks Cove is an Intel board, and if we look at the screen, can you kind of look up at the screen for the Sharks Cove? And scroll down just a skosh, down. There's perfect, stop, don't touch, great. Guess what operating system this is running? Windows 10 for PCs, right? It's got a start menu. It's got multi-windowed apps, right? So that operating system is running on the Sharks Cove. I'm going to do, and I'm going to apply it to shine it on this sensor right here. Can you just show the sensor for a sec? See the sensor? Here it comes. And so now if you can show the screen, the driver is sending those samples up to our desk through the OS, and the app is consuming it. All right, great. Sharks Cove. Holly, let's move over. 18 inches, perfect. 18 inches to my left, you'll see a MinoBoard Max. Max right here, also Intel part, also running a Bay Trail processor. This one is our smallest Windows 10 IoT edition. So we have a very, very minimal edition, which you'll see Steve Teixeira talk about tomorrow, which basically just takes that one core OS and puts a very small amount of machinery to be able to run, to actually get deployed to a box. So this runs a very, very tiny version of Windows 10, and it's on there. And if you see the screen, I don't know why I'm flashing this UV flashlight on the screen. It will have no effect. If you look at the screen, there's no shell because it's an IoT device, which is meant to be a purpose-built device that is not meant for running all kinds of applications, but is meant for running one application at a time. And sometimes only one application ever, depending on what you're doing with your IoT devices. So this is Windows IoT running the exact same driver and the exact same application, and here it comes. There you go. Thank you. Now, let's move another 18 inches over, Holly. And Holly, do not move much further because you'll hit the end of the stage. So, this is the new Dragon Board 410C that Terry talked about in his keynote. Here's the actual board itself, right? And there's our 8016 on there. This thing is buried underneath this overall harness, which has a full touch sensor and allows me to do much more rich device prototyping. But if we were to get underneath there, and I'm not going to ask Holly to do that much gymnastics, right? This board is underneath this demo. So this is running Windows 10 for phones. Same driver, same app. So now let me find my sensor. Let me turn my flashlight on. Away you go. Thank you, Holly. Give it up for Holly. This figure shows what I just showed you. A single application, which was our sensor app, and a single universal driver, which was our sensor driver, and we deployed it on 3 different hardware platforms, running 3 different editions of Windows that were very tailored to a particular user experience and device form factor, right? But as far as you folks are concerned, you write a single driver, you write a single app, and we bring it to bear on all these platforms. I should also make one more statement. We talked a lot in the preparation for this demonstration. We could have picked different boards for different OSs. Do not read too much into this slide. Right, we could have run the IoT on any of these, right? We didn't. We just decided to do the ones we did. So all of these boards are tailored to run any OS that supports that instruction set, and that's kind of the way the system works. One last thing before I look at the slides. If you go back to the middle one of those demos, which was the one that was running the IoT, it was running on the smaller of the Intel boards, which is the MinoBoard Max. I'd like to tell you that at this event at WinHEC, we have a set of lab sessions, which we want you to go get hands-on experience actually writing some of this code. Everyone at WinHEC who attends one of the labs will get a free MinoBoard Max. They'll come in this nice attractive box, and they'll look like that with blinking lights. All right. Great. Most of what we've talked about so far has been very, very, very focused on drivers. Driver this, driver that, app this, app that. Our device platform obviously works very hard. We spend a lot making sure that the driver experience is great, that the quality of the drivers is great, that the customer experience with those drivers is great. But it turns out to build a device, it's not just drivers. So what I'd like to do is talk a little bit about some of the other investments we do, right, which are really about the end-to-end experience of building a device. And as you know, when you build an actual device that someone goes to a store and buys and does something with, how that device is constructed, how the contents of all the software assets on the thing are constructed is important, and how that thing actually gets manufactured is also critically important. So one of the investments we're making that's unique to Windows 10 is we're investing deeply in this thing called Full Flash Update, or FFU. And so with FFU, this is a new capability we're bringing to all of the editions. We had it on Windows Phone prior to Windows 10, and we're bringing that technology to all of our device families with this release. With FFU, it's a very optimized mechanism for going off and imaging and manufacturing machines. And so with FFU, we have the ability to construct an OS image out of various packages that Microsoft provides or that your OEMs or the IHVs provide, and producing a single FFU that we can then rapidly go deploy either on the factory floor, on the device, or on actual disk images. Let me talk about how it works. When you get your MinnoBoard Max and you want to go do something with it, you'll go write a driver, perhaps. You'll go write an app, probably. But then ultimately, you're going to want to be able to package that thing up and then hand it out to your friends or go make, 100 million of them. So let's talk about how that works. You'll get some OS packages from us, right? Microsoft delivers to people who are building devices packaged versions of the components in Windows so that you can then go configure that to go build your devices. And you'll describe those packages in these things we call feature manifests. You'll also get this thing called a board support package, or a BSP. And a BSP has all of the drivers that you got from the board maker. So there's a BSP for the MinnoBoard Max, right, that is not part of Windows proper, but it's jointly developed with us and Intel to make sure that when you have a MinnoBoard Max, you've got all the drivers you need that are unique to this device. Then, and of course, these are described with feature manifests. You then, of course, will want to go write drivers. You'll go bundle those up and write those down in feature manifests. And then finally, you'll want to put some apps on the device, and you'll write those hopefully as appexes. Those are our universal apps, right? And you'll write those down in a different kind of file called an OEM customization. And then all of this stuff gets wrapped up in this file, which we call OEM input. And OEM input.xml is the roadmap of all of the OS packages, the BSP components, the drivers in the application. That's the roadmap for what you want the thing to look like. You then run this thing through one of two tools. We have this thing called the Windows Imaging and Customization Designer, or ICD. This is a tool that gives you a graphical interface over all of those files that we talked about. Or those of you who have these files already or like to go edit them in the text editor of your choice or your XML editor of choice, you can do that as well. And we have a command line version of all this packaging machinery called Image App. And when I run Image App or ICD against all of this input, what happens is I get a single file. I get a single linear array of bytes, which represents on a sector-by-sector basis the contents, the disk layout of my target device. Multiple partitions, all the partitions and volumes are laid out. All of those XML files give me the ability to control which partitions and volumes each of the files goes on to, as well as the paths into the file system. And that FFU then is the thing I can then go take off and throw into my factory floor. I could go put it on the web if I was a maker and just say, here, if you want to go flash your Raspberry Pi or your Minno board, you can go do it with this. But this FFU format is really kind of the way we're bringing all of the Windows devices together in terms of imaging and manufacturing. Now, once I've got an FFU, what do I do with it? Once I've got an FFU, there are two important things I can actually go do with it. One thing I can do is I can actually go flash live devices. So we have the ability through this thing called FFU tool, which we've shipped in phone before, but now we make it available on all Windows devices, including on PCs. FFU tool allows me to tether up to 8 devices and go push this thing out to an actual live device. And there's a small amount of UFI code I need on the recipient device to be able to process this, and away we go. And we'll talk, if you go to the sessions on manufacturing, we'll give you more detail as to how to do that. So I can go flash live devices, or I can use DISM to actually just go write that FFU onto a piece of storage. So why don't I do one more demo, and then we'll wrap up. So I've got a command line prompt. We talked about whether it would be interesting to look at the XML. Believe me, there are lots of XML angle brackets. And if you want to follow me up after this talk, I'm happy to walk you through it. For now, let's just ignore them. But I've got a script in here which I'd like to show you. Here's a script that runs the two commands we just talked about. That first command, ImageGen, basically says, I'm going to read the OEM input.xml, and I'm going to read the OEM customization.xml. Those two XML files describe the OS packages and BSP packages and the applications. And I'm going to scrunch those things down, and I'm going to write them into an FFU, which is output.ffu. That's right there. So when I run that first command, it will go read all of the OS packages, which I've put in as part of my kits when I installed all the kits, the development kits on my box, and all my customizations to it, and scrunch it into a single FFU. Once this command completes, and it takes a few minutes, so I won't be able to actually finish it while we're in this talk, I then take this other tool called DISM, right, which then says I'm going to read output.ffu, which you see here, and I'm going to go apply it to a drive, which in this case I've got a physical device called Physical Drive 2. So I'm going to go ahead and run this thing. And it's off building. Now, this thing will take a few minutes, and we're almost out of time in this talk. What I'd like to do is we ran this tool right before we came up here, and we actually took that FFU, which is the exact same one that we had on those 3 devices. We actually burned it to an SD card. I'd like to just open that SD card up in my Windows right now. So if I go over here, we mounted the SD card on E. And so if we had a few more minutes, I'd be able to do this on the actual image I just created, but this is just a pre-baked one. And you'll notice this is the layout of the boot volume. And if I go to Windows, System 32, drivers, UMDF, because remember we built a UMDF driver, a user mode driver. If I go here, there you'll see CM3512. That's the driver that we actually started creating at the very beginning of this talk, right? And this is how it went from us in Visual Studio typing in some curly braces to us actually having a binary on an image that I can then go flash to devices. Awesome. So, where are we? What we just talked about was how Windows 10 has a universal device platform that allows a single driver to span multiple device families. So you write a driver once, and you can deploy it in all of these different form factors. We saw some of the things we're doing to up-level driver development. Specifically, we talked about WDF. We're also doing a lot of other work. If you go to our hardware dev center, you'll see a lot of the things we're doing. But we talked about WDF and putting that source out on GitHub. We talked about the development boards that we're supporting, and this is just the first round. We're continuing to invest in this area, and we think it's a very important thing that we need in our toolbox and that you need in your toolbox to succeed with Windows. And then finally, you saw that we've got a lot of investment in imaging and manufacturing to kind of normalize the way devices are created and imaged across all these device families. So, I have one more thing. Terry Myerson and I would like to thank you for coming to WinHEC. Enjoy your lunch.
Please enjoy lunch before attending the afternoon breakout sessions. You will find session calendars posted on displays throughout the event venue and may refer to the event guide for additional information and details.